In CART, the value of min-bucket can affect the model's out-of-sample accuracy. As we discussed earlier in the lecture, if min-bucket is too small, overfitting might occur. But if min-bucket is too large, the model might be too simple. So how should we set this parameter value? We could select the value that gives the best testing set accuracy, but this isn't right. The idea of the testing set is to measure model performance on data the model has never seen before. By picking the value of min-bucket to give the best test set performance, the testing set was implicitly used to generate the model. Instead, we'll use a method called k-fold cross-validation, which is one way to properly select the parameter value. This method works by going through the following steps. First, we split the training set into k equally sized subsets, or folds. In this example, k equals 5. Then we select k-1, or 4 folds, to estimate the model, and compute predictions on the remaining 1 fold, which is often referred to as the validation set. We build a model and make predictions for each possible parameter value we're considering. Then we repeat this for each of the other folds, or pieces of our training set. So we would build a model using folds 1, 2, 3, and 5 to make predictions on fold 4. And then we would build a model using folds 1, 2, 4, and 5 to make predictions on fold 3, etc. So ultimately, cross-validation builds mini-models, one for each fold and possible parameter value. Then, for each candidate parameter value and for each fold, we can compute the accuracy of the model. This plot shows the possible parameter values on the x-axis and the accuracy of the model on the y-axis. This line shows the accuracy of our model on fold 1. We can also compute the accuracy of the model using each of the other folds as the validation sets. We then average the accuracy over the k folds to determine the final parameter value that we want to use. Typically, the behavior looks like this. If the parameter value is too small, then the accuracy is lower because the model is probably overfit to the training set. But if the parameter value is too large, then the accuracy is also lower because the model is too simple. In this case, we would pick a parameter value around 6 because it leads to the maximum average accuracy over all parameter values. So far, we've used the parameter min-bucket to limit our tree in R. When we use cross-validation in R, we'll use a parameter called CP instead. This is the complexity parameter. It's like adjusted R-squared for linear regression and AIC for logistic regression in that it measures the trade-off between model complexity and accuracy on the training set. A smaller CP value leads to a bigger tree, so a smaller CP value might overfit the model to the training set. But a CP value that's too large might build a model that's too simple. Let's go to R and use cross-validation to select the value of CP for our CART tree. In our R console, let's try cross-validation for our CART model. To do this, we need to install and load 2 new packages. First, we'll install the package caret. You should see some lines run in your R console, and then when you're back to the blinking cursor, load the package with library caret. Now, let's install the package E1071. So again, install.packages, and in parentheses and quotes, E1071. Again, you should see some lines run in your R console, and when you're back to the cursor, load the package with library E1071. Now we'll define our cross-validation experiment. First, we need to define how many folds we want. We can do this using the train control function. So we'll say num folds equals train control, and then in parentheses, method equals, and in quotes, CV for cross-validation, and then number equals 10 for 10 folds. Then we need to pick the possible values for our CP parameter using the expand.grid function. So we'll call it CP grid, and then use expand.grid, where the only argument is .cp equals SEQ for sequence 0.01, 0.5, 0.01. This will define our CP parameters to test as numbers from 0.01 to 0.5 in increments of 0.01. Now we're ready to perform cross-validation. We'll do this using the train function, where the first argument is similar to that when we're building models. It's the dependent variable, reverse, followed by a tilde symbol, and then the independent variables separated by plus signs. Circuit plus issue plus petitioner plus respondent plus lower court plus unconstitutional. Our data set here is train with a capital T, and then we need to add the arguments method equals, and in quotes, our part, since we want to cross-validate a cart model, and then tr control equals num folds, the output of our train control function, and then tune grid equals cp grid, the output of the expand.grid function. If you hit enter, it might take a little while, but after a few seconds you should get a table describing the cross-validation accuracy for different CP parameters. The first column gives the CP parameter that was tested, and the second column gives the cross-validation accuracy for that CP value. The accuracy starts lower and then increases, and then will start decreasing again, as we saw in the slides. At the bottom of the output, it says accuracy was used to select the optimal model using the largest value. The final value used for the model was CP equals 0.18. This is the CP value we want to use in our cart model. So now let's create a new cart model with this value of CP instead of the min bucket parameter. We'll call this model Stevens Tree CV, and we'll use the rPart function, like we did earlier, to predict reverse using all of our independent variables, circuit, issue, petitioner, respondent, lower court, and unconstitutional. Our data set here is train, and then we want method equals class, since we're building a classification tree, and CP equals 0.18. Now let's make predictions on our test set using this model. We'll call our predictions predict CV, and we'll use the predict function to make predictions using the model Stevens Tree CV, the new data set test, and we want to add type equals class so that we get class predictions. Now let's create our confusion matrix using the table function, where we first give the true outcome, test reverse, and then our predictions, predict CV. So the accuracy of this model is 59 plus 64 divided by the total number in this table, 59 plus 18 plus 29 plus 64, the total number of observations in our test set. So the accuracy of this model is 0.724. Remember that the accuracy of our previous CART model was 0.659. Cross-validation helps us make sure we're selecting a good parameter value, and often this will significantly increase the accuracy. If we had already happened to select a good parameter value, then the accuracy might not have increased that much. But by using cross-validation, we can be sure that we're selecting a smart parameter value.